You can do thought experiments. You can actually perform these in real life, but you can do thought experiments involving this kind of wave-particle duality, the idea that an electron behaves both as a particle and as a wave at the same time. So we've encountered this before, right? We have a plane wave front, hits a screen, and there are two slits, and each of those slits acts like a point source of waves coming out, according to Huygens' principle. Those waves interfere and give you a pattern of light and dark spots on the screen beyond. You did this in DL and everything. Did it in lecture here. So we know this works for photons. Photons are certainly waves. Now, if particles are also acting as waves, we ought to be able to create a slit for, let's say, a beam of electrons coming in. A pair of slits, they would have to be very, very close to each other because, as we saw, the wavelength of our electrons, if they have even 100 volts, right, was already a tenth the size of an atom. So we have to use pretty low energy electrons and slits that are nanometers apart. Nevertheless, such an experiment is in principle possible. And what would happen, though? If we have a beam of electrons, yes, you would see a pattern of light and dark spots as to the preferred directions as they pass through the slits, as if they were waves with the de Broglie wavelength interfering with each other in that certain direction. D sine theta equals n lambda. You remember that relationship between for diffractions. In fact, we can do electron diffraction in a very, remember how we went from the two-slit experiment to the multi-slit experiment, and multi-slit is a diffraction grating, right? And you can actually use a crystal of atoms all lined up in nice rows and columns on the surface that acts like a diffraction grating for electrons. In fact, they're doing it upstairs in various of the labs here. In fact, on the third floor, Professor Jiandong Zhu is doing low-energy electron diffraction off of crystallized, biologically relevant molecules like proteins and so forth, trying to unravel the structure of them using this low-energy electron diffraction. And what he does is he shines a beam of electrons on these crystals and looks at the diffraction pattern of electrons coming off. So this actually happens. I mean, you can actually take electrons, shoot them at a diffraction grating, which is made of a crystal, and see a diffraction pattern. So yes, electrons do have this wave-like nature, and you can show it very easily. The freaky thing about quantum mechanics, though, is that you can turn down the beam intensity to the level where you have just one electron at a time hitting that crystal, and you still get a diffraction pattern. It's not like it's a little ball bouncing off the surface of that crystal. It's like it's a wave itself, interfering with itself. It itself is spread out in space over that. Turns out in our thought experiment, if you close one of these slits, then you lose the diffraction pattern. And people have actually done this with, electrons passing through tiny, tiny, tiny slits and done that. So that's something to ponder in trying to understand the deeper nature and implications of quantum mechanics in our world. There's plenty of popular literature written on this subject. But you're thinking, oh my gosh, the final exam's in less than 2 weeks. What do I need to know about quantum mechanics for the final exam? And here it is. The stuff on this slide is what you will be tested on. You got to know that light comes in quanta that we call photons. Each photon has an energy of 1240 eV nanometers divided by its wavelength. There's only so many ways we can ask our questions, right? You either give you the wavelength and you calculate the energy, or give you the energy and you calculate the wavelength, just by inverting this equation for that. Pretty straightforward. You got to know that atoms emit and absorb light, photons, at very certain energy, discrete energies corresponding to transitions between different energy levels. And we saw the energy levels of the hydrogen atom. And you'll discuss that further in DL, so forth. Lastly, that particles do act like waves and have a wave nature with wavelength lambda is h over p. So one way that we asked this question, for example, a couple years ago on one of the final exams, and it's in the practice exams that I've posted online now, is suppose you have an electron confined to what we call a nanowire. A nanowire is nanometers in width, but it's, let's say, 1 micrometer, 1/1,000,000th of a meter long, which is 1,000 nanometers. So it's like you can imagine it being 1,000 atoms long and 1 atom wide. Okay, so electron's confined to that, meaning it can't get off the ends. Okay, so you think, well, an electron acts like a wave. What other wave is confined at the ends? Oh, right, a wave on a string, right? So you think you have modes that look like a single mode with wavelength 2L, and then 2 humps with wavelength L, etc. So you can define the energy levels of such an electron confined to that region just in terms of waves on a string, for example. We'll go over that problem next week when we go over the practice exam. Basically, you should keep these ideas in mind as you go through DL and study these ideas in depth. But this is anything that we ask you is going to use one of these two equations, and the ideas, the concepts of the wave-like nature of particles one way or another. We're not going to ask you to solve the hydrogen atom or something like that.